Hi everyone, welcome back to chemistry. Today we're going to start Unit 7 on chemical formulas. We're going to learn first how to write formulas of ionic compounds. Keep in mind that a chemical formula will always have a neutral charge, so we don't see pluses or minuses for our superscripts. There are no superscripts in our formulas. They also show the types of atoms and how many there are of each type of atom. So to write an ionic compounds formula, we need to know the two types of ions that are involved and the charge on each of those ions. So let's look at some. Sodium and fluorine are the first ions we're going to look at. Sodium is in group 1, so when it forms an ion, it has a charge of +1. Fluorine's in group 17, so it forms an ion with a charge of -1. So keep in mind, sodium is looking to lose an electron and fluorine is looking to gain an electron. So the two of them make a perfect pair. For every one sodium, it wants to find one fluorine, and it will do that and make the formula NaF. Barium is a group 2 metal, so when it forms an ion, it has a charge of 2+. Oxygen's a group 16 nonmetal, so when it forms an ion, the charge is -2. So barium's looking to lose 2 electrons, and every oxygen is looking to gain 2 electrons. So for every one barium, it needs to find one oxygen. So the formula then is BaO. Sodium looks to form an ion with a +1 charge. Oxygen looks to form an ion with a -2 charge. So what that means is oxygen will need 2 sodium ions for every one oxygen ion. So the formula in this case is Na2O. Last example, barium is 2+, fluorine is only 1-, so every barium ion will need to find 2 fluoride ions. And when it does, the formula becomes BaF2. So those are how we write an ionic compounds formulas. We can also use the Criss-Cross Rule, where we take the charge on the cation, for example, and that becomes the subscript of the anion. This is not my favorite way to do this because you don't always get the right answer in certain circumstances. But let's look at it because it's a quick, easy thing to figure out. Let's say we have the aluminum ion and the oxide ion. If we just write Al and O and we crisscross those numbers, so the 3 from the aluminum becomes the subscript on the oxygen, the 2 from the oxygen becomes the subscript on the aluminum, our formula is Al2O3. Let's look at another example, barium ion and sulfide ion. If we crisscross those charges, we get Ba2S2. However, you have to be careful. Warning, you always have to reduce to the lowest terms. So if this is the formula you get when you crisscross, and you keep that formula as Ba2S2, you would get it wrong because that is not reduced to the lowest terms. So the correct formula would be Bas. Okay, for every one barium, we only need one sulfide ion. Every one barium ion needs one sulfide ion. So make sure you reduce to lowest terms, which this is one of the reasons I don't like the crisscross rule because you might forget to do that. Another reason has to do with when we have polyatomic ions, which we'll talk about later. Here's another example. If we crisscross those numbers, we get InBr3, and that's the formula. So let's look at some specific examples when we have single charge cations with main group anions. The main group anions are the ones that are pulled off the table for the anions. The single charge cations are going to be the ones in groups 1, 2, 13, and silver, cadmium, and zinc. So groups 1, 2, 13, silver, cadmium, and zinc are in gray boxes. You must memorize those charges for those 3. So memorize that silver, when it forms an ion, will have a +1 charge, cadmium, when it forms an ion, will have a +2 charge, and zinc, when it forms an ion, will have a +2 charge. Those are the only charges those three ions will have. Silver is always +1, cadmium is always +2, zinc is always +2. Notice where they are on the table as well, because that might help you remember which ones they are that have those single charges. Group 1, we know, always forms an ion with a +1 charge. Group 2 is +2. Group 13 is +3. So to name these types of ionic compounds, given the formula, what we do is we write down the name of the cation, then the anion name goes after it, and change the ending to "ide." So NaF, the cation is sodium, and then fluorine is the anion. We just change the ending to fluoride. Notice the IDE here. Barium, and then oxygen becomes oxide, so it's barium oxide. Sodium oxide, and barium fluoride. So again, you write the name of your cation and then the name of your anion, but change the ending of the anion to IDE. To write the formula given the name, you first write the symbols for the two types of ions, and then balance your charges to write the formula. Let's look at some examples. Silver is +1, right? We said that you have to memorize that one. Sulfide, this just means it was sulfur from the periodic table. So silver is +1. Sulfur is in group 16, so the charge is 2- when it forms an ion. So for every one sulfide, we need 2 silver ions to balance the charges. So it becomes Ag2S. Zinc is one of those ones we have to memorize, is 2+. Phosphide just means it's phosphorus from the periodic table, which is in group 15. So the charge it has when it forms an ion is 3-. So we need 3 zinc ions for every 2 phosphide ions. Calcium is in group 2, so it forms an ion with a 2+ charge. Iodide is just iodine, so that's going to form an ion with a -1 charge. So we're going to need 2 iodide ions for every 1 calcium ion to balance the charges. Notice in our 3 formulas that we just found, there are no positives or negatives. When we write our chemical formulas, we don't have any pluses or minuses in them. Now let's look at multiple charge cations with our main group anions. So the main groups, again, are pulled off the table for the anions. The multiple charge cations are going to be the ones that we've kind of skipped, basically our D block elements plus lead and tin. So Pb is lead, Sn is tin. So they're in red here on the periodic table. Notice we're not including silver, cadmium, or zinc, because silver is always +1, cadmium and zinc are always +2. Right now we're talking about cations that can have multiple charges. Silver, cadmium, and zinc do not have multiple charges. They only have a single charge, whether it's +1 or +2, but they don't have multiple charges. So to name them, given the formula, first you figure out the charge on your cation, then you write the name of the cation, then you write Roman numerals in parentheses, not brackets, to show the cation's charge, and finally write the name of the anion. So we have 4 examples we're going to look at. So first we have FeO. We need to figure out the charge on the cation. We know it's iron, and we know it's oxide. Same is true for Fe2O3. For the bottom 2, we know it's copper bromide. But because iron and copper have multiple charges, we have to figure out which charge we're referring to in these formulas. So for FeO, we don't know the charge of iron, but we do know that oxygen, when it forms an ion, has a charge of 2-. So if it's a 1-to-1 ratio of iron to oxygen, that must mean that iron has a 2+ charge because that makes it neutral. So then the name becomes iron 2 in parentheses oxide. Notice it's a Roman numeral. We want to have Roman numerals in our parentheses. Next one, we have Fe2O3. So there's 2 iron ions, there's 3 oxide ions. Each oxygen ion has a -2 charge. So in total, it's -6. So we have to balance that with the positives. So that if there's only 2 irons, they each must be +3. So the formula becomes iron 3 oxide. Let's look at the next one. Copper, we're going to figure out. Bromine is a halogen, so it's -1. Since it's a 1-to-1 ratio between copper and bromine, it's going to be copper 1. So copper 1 bromide. And then the last one, there's 2 bromide ions, each are a -1 charge, so the copper must be +2. So copper 2 bromide. So let's look at this a little bit closer. Iron 2 oxide, iron 3 oxide. That's telling us that iron can be either a +2 ion or a +3 ion. So we had to go through these steps to figure out which one it was. Copper could be a +1 or a +2. Again, we had to go through these steps to figure out which one. The reason we need Roman numerals is because the elements in red on the periodic table on this slide have multiple charges. So again, that's mostly our D block, but not including silver, zinc, or cadmium. But it does include lead and tin, even though they are not in the D block. How do we find the formula given the name? We write the symbols for the 2 types of ions, then balance charges to write the formula. Let's look at these examples. So we have cobalt 3 chloride. So they're telling us that cobalt has a 3+ charge. That's what the Roman numeral says. And chloride is just chlorine with the ending changed. So chlorine has a -1 charge. So we're going to need 3 chlorines for every 1 cobalt. So the formula is COCl3. Tin 4 oxide, the Roman numeral is telling us that tin has a 4+ charge. Oxide means it's just oxygen from the periodic table. So that's 2-. So we're going to need 2 oxide ions for every 1 tin ion. So the formula is SnO2. Tin 2 oxide is telling us that the charge for tin is 2+. Oxygen, when it forms an ion, is 2-. So the formula is just SnO. Again, you'll notice there's no charges in our final formulas. These are the formulas. Here's a list of common polyatomic ions. Many of them that you're going to need for practice problems are in here. There's a few that aren't on here that were on the handout you were given a few units back on polyatomic ions that you would be given at all times for assessments. So those have a couple on there that aren't on this list, but all the ones you have to memorize were on that list, and the same ones that you have to memorize are on this list. They're in red. One thing I want to point out that might help you as you talk about polyatomic ions and their formulas, if you'll notice, nitrate has 3 oxygen atoms. Nitrite has 2, 1 less than nitrate. Let's look at phosphate, has 4 oxygen atoms. Phosphite has 1 less, or 3 oxygen atoms. Let's look at chlorate. Chlorate has 3 oxygen atoms. Chlorite has 1 less, or 2 oxygen atoms. I skipped sulfate over here. It has 4 oxygen atoms. Sulfite has 3 oxygen atoms. So you should notice that ites have 1 less oxygen than ates. That's one pattern I want you to notice. Another pattern I want you to notice is the prefix per. If you look at chlorate, it's ClO3-. Perchlorate is ClO4. So when there's a per, there's one more oxygen. Another example, if I were to put oxide up here, oxide has one oxygen atom, but peroxide has two. So those are some of the patterns I want you to notice, and they'll help you as you talk about polyatomic ions and try and figure out what their formulas are. So how do we write formulas with polyatomic ions? Keep in mind that parentheses are required when you need more than one bunch of a particular polyatomic ion. If you don't need more than one, you must not put parentheses. So let's look at barium ion, and this is the sulfate ion. So we see that barium has a 2+ charge and the sulfate has a 2- charge. So we need one barium for every one sulfate. Mg2+ and NO2-. So we see that we're going to need 2 of the NO2 groups for every 1 Mg. So we're going to have to use parentheses around the NO2. And then as a subscript, you see it here, I'll circle it, there's 2 NO2 groups. This is one of the reasons I don't like the crisscross rule, because if you crisscross your charges and you bring the 2 down here, a lot of students don't know what to do with the 2. Some will change it to NO4, some will do N2O4. Those are not correct. It should be written as it is on the screen. So that's one of the reasons I don't like crisscrossing, or at least a second reason I don't like crisscrossing. NH4+, ClO3-. We need 1 NH4 for every 1 ClO3, so there's no parentheses, and the formula is written like that. SN4+ and SO4 2-. So we're going to need 2 SO4 groups for every tin ion. So we have to have parentheses. Again, these are parentheses, not brackets. The next one, we're going to need parentheses again. We're going to need 2 iron atoms for every 3 dichromates. And then the last one, we're going to need 3 ammonium ions for every 1 nitride ion. So again, you see here that we only use parentheses when there's more than one group of that polyatomic ion. So let's focus on the polyatomic ions and the compounds they will be in. We're going to insert the name of the ion where it should go in the compound's name. So let's write some formulas. Iron 3 nitrite. First, I want you to recognize that because this ends in ITE, it is not nitrogen from the periodic table. If it were nitrogen from the periodic table, it would end in IDE. So because it's not IDE and it's ITE, that tells me that this is a polyatomic ion. So if I look up in my list here, I see nitrite. It's NO2-. And we've color coded these. So green color in these names refers to a polyatomic ion. But when you have practice problems, we're not going to have them color coded. But I just want you to see here, the green represents polyatomic ions. Phosphide in this second example is blue because it comes from a blue block on the periodic table. The gray zinc comes from a single charge cation. And then the red iron 3 and lead 2 come from the multiple charge cations. So iron 3 nitrite is Fe3+. Nitrite we see from our table is NO2-. So we're going to need 3 nitrites for every 1 iron with a 3+ charge. So the formula is FeNO2 3. Next one, ammonium. Ammonium you're not going to find on the periodic table, but ammonium is that polyatomic ion, one of the ones you were supposed to memorize. So that's NH4+. Phosphide, because it ends in IDE, I know it comes from the periodic table and it's phosphorus. So ammonium is NH4+. Phosphorus is P3-. So we're going to need 3 ammonium ions for every 1 phosphide ion. So we have to have parentheses for the 3 ammonium ions and then the phosphorus. Again, notice in our final formulas, we don't have any pluses or minuses. Ammonium chlorate, this is not chlorine from the periodic table because it doesn't end in IDE, it ends in ATE. So chlorate is one of the polyatomic ions you're supposed to memorize, but if you forgot, it's up here on our table, CO3-. Ammonium we know is NH4+, so we write down those ions, figure out their ratio. It's a 1-to-1 ratio, so we don't have any parentheses, and the formula is NH4Cl O3. Zinc, even though it's in the D block, it always has a +2 charge, so that's why we don't see a Roman numeral in the name. The ion is Zn2+. Phosphate is the polyatomic ion. It's not phosphorus. You were supposed to memorize that. In case you forgot, it's right here. PO4 3-. So Zn3PO4 2. Last one, lead 2. So that's Pb2+. Permanganate is MnO4-. So we're going to need 2 permanganate ions for every 1 lead 2+ ion. So we need to have parentheses. So those are the formulas. Now let's write the names from the formulas. Again, we're color coding to help you figure this out, but you're not going to see color coding again. It's only in our PowerPoint. So make sure you're understanding where these charges are coming from and why. So our first example, NH42S2O3. We know NH4 is our ammonium polyatomic ion. S2O3 is not on our table, but that's thiosulfate. That was on a prior table. When you were given a list of polyatomic ions that you had to memorize, you were also given a list of the ones that would be given to you. On that list was thiosulfate. Next one, AgBrO3. So we know Ag is just silver. BrO3 is bromate. That is up here on the table. So it's silver bromate. Notice we're not changing the endings of our polyatomic ions. Whatever those names are for the polyatomic ions, they always stay the same. Don't change their endings. Next one is ammonium. And then N is just nitrogen, so we change the ending to IDE. So ammonium nitride. Next one is uranium, which is a transition metal. It's actually in the F block. We do need to figure out the charge of it. So we have uranium, and then we have chromate. So we have 3 chromate ions. So that's a total negative charge of 6-. So therefore uranium must be 6+. So the name of it is uranium-6 chromate. That is your Roman numeral for 6. In case you're wondering, the Roman numerals are for 1, it's just a capital I. 2 is like that. 3 are 3 vertical lines. 4 is a vertical line and then a V. 5 is just a V. 6 is VI, like we see right here. 7 is VII. 8 is VIII. 9 is IX. And 10 is X. And then our last example is chromium. This is the sulfite polyatomic ion. So we need to know what the charge is of the chromium. If there's 3 sulfites with the 2- charge for each one, chromium then must have a charge of 3+. So chromium 3 sulfite. So that's it for naming our ionic compounds. I know there's a lot of rules and different things to pay attention to, so it's really important that you practice. And if you have questions, please make sure you ask questions. Now let's look at covalent compounds. Remember that ionic compounds had a cation and an anion. Covalent compounds have 2 types of nonmetals. So recall that our nonmetals are in blue on the periodic table. And what's really important here is that we don't need to worry about any charges. In fact, doing covalent compounds, naming and formulas are a lot easier than ionic compounds. So you'll be happy about that. So what do you do if you have a covalent compound? You're going to use Greek prefixes to indicate how many atoms there are of each element. When you write down the name of the formula, never use the prefix mono on your first element. So the prefixes you have to memorize: 1 is mono, 2 di, 3 tri, 4 tetra. Be careful, this is the one that a lot of students get wrong, because in math class you learned a different prefix, and I'm not going to mention it here because I don't want you to get confused, but 4 is tetra. 5 penta, 6 hexa, 7 hepta, 8 octa, 9 nona, 10 deca. Memorize those prefixes. All right, we've got 6 examples. First one, we're given a name. We have to figure out the formula. So there's no prefix in front of carbon. So therefore we know there's just 1 carbon. And in front of oxide, that's oxygen, we have the prefix di, which is 2. So the formula is CO2. Next one, CO. So there's 1 carbon. We're not going to say monocarbon. We don't put mono on the first word. So it's just carbon. And then there's 1 oxygen. It's monoxide, as you all probably knew already. CO is carbon monoxide. Notice we don't say monooxide. We're not going to put 2 O's next to each other in the name. Next one, dinitrogen. So that's 2 nitrogens. Notice we did not change the ending on the first word. Trioxide. So 2 nitrogens, 3 oxygens. And you also write them in this order. So nitrogen has to be before oxygen. Don't do it the other way around. N2O5. So there's 2 nitrogens, so we're going to use a prefix. It's dinitrogen, and then pentoxide. So just like the second example where we had monoxide, we don't put 2 O's next to each other. We also don't say pentaoxide, AO. Get rid of the A and just call it pentoxide. Next one, carbon, there's no prefix, so it's just 1 of them. Tetra is 4. Chloride is chlorine. So CCl4. And the last one is nitrogen triiodide. Here we do keep 2 I's next to each other. I know we have so many rules in chemistry, it's hard to keep track. So just to go over this again, don't put mono on the first word if there's only 1 of them. Never change the ending of the first word. On the second word, change your ending to IDE and put the prefix on it. You have a prefix on the first word if there's more than 1 of them, but if there's not, then you don't. There will not be any polyatomic ions when we talk about covalent compound naming. So our third category are acids. So I know we've talked about ionic and covalent compounds before, and we really haven't talked about acids. This is our first introduction to acids, and we're going to start out with nomenclature of acids. Nomenclature is just naming. So you first have to identify that you have an acid. How do you do that? Acids will begin with the letter H. Binary acids will have only 2 elements. So binary has 2 elements in the formula. So you know the first element is always the hydrogen. Then you have to identify what the second element is. So the one that isn't hydrogen. Once you identify the second one or the other one, change the ending of that to IC. Then put hydro in front, add the word acid at the end. Let's look at an example. HCl. So this is binary because we have hydrogen and chlorine. So there's only 2 elements, so it's a binary acid. So the other element is chlorine, so we're going to change the ending to ic. So chlorine becomes chloric. Put a hydro in front of that, and then add the word acid, hydrochloric acid. HCl, hydrochloric acid. HF, again, this is binary. The other element is fluorine. So fluorine becomes fluoric. So we say hydrofluoric acid. Here are some other binary acids because there's only 2 elements. So again, they'll start with hydro. We'll change the ending. So bromine becomes bromic. Iodine becomes iodic. Sulfur becomes sulfuric. And then acid. What if it's not binary? Here are some examples. H3PO4, we see a polyatomic ion, hopefully you recognize that, in there, or ClO3. So these are oxyacids with a polyatomic ion in them. You have to identify your polyatomic ion. Then, if the polyatomic ion ends with 8, it becomes an ic acid. So H2SO4. SO4 is the polyatomic ion sulfate. So sulfate obviously ends in 8, so we change it to sulfuric acid. There's no hydro. When there's that polyatomic ion, there's no hydro. So just sulfuric acid is the name for H2SO4. HNO3, we recognize hopefully the polyatomic ion there. That's our nitrate polyatomic ion. So it ends in 8. We're going to change it to ic acid. So it's nitric acid. Now, not all polyatomic ions end in 8. Some will end in ite. So if it ends in ite, we change it to OUS acid, H2SO3. So remember H2SO4, which we just saw right here, has the sulfate polyatomic ion. 1 less oxygen is sulfite. So ite becomes OUS. So it's sulfurous acid. HNO2, so again, before we had HNO3, right here, now we're doing 1 less oxygen. So NO3 was nitrate, 1 less oxygen is nitrite. Ite becomes OUS, and then acid, nitrous acid. Let's look at these examples. HBr, that's binary, so we're going to have hydro, and then bromine, change the ending to ic acid, hydrobromic acid. H3PO4 is a polyatomic ion, that's phosphate, so 8 becomes ic acid, so we call it phosphoric acid. So it was phosphate, it becomes phosphoric acid. HClO4, ClO4 is the perchlorate polyatomic ion, so it ends in 8. So we're going to change it to perchloric acid. H2S is binary, so we're going to say hydrosulfuric acid. HClO2, that has the chlorite polyatomic ion, so it ends in ITE. So we change that to OUS acid, so it's chlorous acid. So this gets really confusing. I get it. We have a little trick on how to help us remember how to change the endings. So there's a couple tricks. This is one of them. Notice what's in blue. I ate an acid and it was ic. So if it ends in 8, it becomes ic acid. And I might, ITE, be nauseous, OUS. So I ate an acid and it was ic, and I might be nauseous. 8, ic acid, ite, OUS acid. I have a different way of remembering it that is a little bit shorter and easier for me, especially because I like ice cream. So the way I remember it is I ate ice cream and it was delicious. I ate ice cream and it was delicious. So ate, ick, it, with the E at the end is your ite, O-U-S. So I ate ice cream, so ate becomes ick, and it was delicious, so your ite becomes O-U-S. That's what I like to remember. So here we have H3PO4. So PO4, think about that. What's the name of the polyatomic ion? It's phosphate. So it becomes ic acid, phosphoric acid. H2SO3. SO3 is sulfite. Ite becomes OUS acid, so sulfurous acid. So that ends our naming. And these are rules that you're going to have to follow all year long. You'll get used to it. I know at first it might seem painful to figure this all out because it's a lot to remember. But like with anything else that you do, the more you practice, the better you'll get at it. So keep practicing it and trying it and you'll get it. It's very repetitive. Seems like there's a lot of rules, but once you get into it, it's not so bad. Now let's look at some calculations. Now that we know how to name things and know what their formulas are, we can do some calculations and talk about different substances. We're going to look at 5 different types of calculations. Some of them, like the first one, molar mass, we've already seen before, so it's kind of more of a review. Percentage or percent composition is pretty simple. I think you'll catch on to that pretty quickly. Empirical formula, I've got a little poem to help you remember the steps in that. Molecular formula will be a piece of cake after you do empirical formula. And then after you've done that, finding the formula of a hydrate is pretty simple too. Just, again, a lot to remember, but the more you practice, the better you'll remember it. All right, let's start with molar mass. That's the mass of 1 mole of a substance. So let's say we have lead 4 oxide. By the way, are you wondering how I knew it was lead 4 oxide? Well, I know that oxygen will form an ion with a 2- charge. So if I have 2 oxygens and they each have a 2- charge, that's an overall negative charge of 4-. If there's only 1 lead ion, it must have a 4+ charge. So that's lead 4 oxide. I have to say the number 4 because lead is one of those cations that can have multiple charges. So we're going to list out each type of atom we have. We have 2 different types. We're going to say how many there are of each one, which we can look at the formula to figure out. And then we go to the periodic table, look up lead, it's atomic number 82. Oxygen is atomic number 8. So we know in every mole for lead, there's going to be 207.2 grams, and for oxygen, 31.98 grams. When you add them together, the molar mass is 239.18 grams for every mole of PbO2, HNO3. So there's 3 different types of atoms. By the way, this is an acid because it starts with an H, right? Remember that anytime we see a formula start with an H, it's an acid. So there's 1 hydrogen, 1 nitrogen, 3 oxygens. Go to the periodic table for each one, write down their masses for a mole. Multiply and then add together, you get 62.99 grams per mole. Molar mass is always grams per mole. So when someone asks you for the molar mass, make sure your units are always grams per mole. Make sure you include your substance. Remember, numbers, unit, substance every single time. Ammonium phosphate. So now that we learned how to write formulas from names, we should be able to figure out what the formula is and then calculate the molar mass. So ammonium is not an element on the periodic table. That's one of the polyatomic ions you had to memorize. Phosphate is also the polyatomic ion. 1, you had to memorize it, but 2, it ends in 8, not IDE. So ammonium is NH4+. Phosphate is PO43-. So we need to have 3 ammoniums for every 1 phosphate, so the charges will balance. So that's our formula. Make sure to put parentheses around the ammonium. So we have 4 different types of atoms. Make sure you count these correctly. There's 3 nitrogens, because if there's a 3 outside the parentheses, you're going to take that and multiply it by every subscript inside the parentheses. So 3 times 1 for nitrogen is 3 nitrogen atoms. 3 times 4 for hydrogen is 12 hydrogen atoms. 1 phosphorus atom and 4 oxygen atoms. Then go to the periodic table and write down their masses. You're going to multiply those together and then add the totals. And that's how many grams there are in every mole of NH43PO4. That's molar mass. Not bad, we've done it before. The tricky part is just maybe writing the formula from the name, or maybe remembering how to multiply when you have parentheses to figure out how many atoms you have of each type. Next type of calculation is percentage composition, sometimes called percent composition. That is the percent by mass of each element in a compound. Because it can get a little tricky with sig figs depending on what periodic table you look at, and really there's no other numbers to determine sig figs for in these problems, we will always round our answers to 2 decimal places. The formula we use for percent composition is the percent of an element is equal to the grams of that element divided by the mass of just 1 mole of the compound times 100. So this is similar to, I'll give you an analogy, if I have a cake and I cut it into 10 slices. If I eat 1 out of 10 of those slices, I have eaten 10%. So if I have a compound with 2 elements, I figure out the mass of one of those elements in the compound divided by the total mass of 1 mole of that compound times 100, that gives me the percent of that element. Find the percent composition. So we're going to use the calculations on the prior slide. So we had PbO2. We found the masses of the lead and the oxygen. So lead, there was only 1 atom, so the mass was 207.2 grams from the periodic table. Oxygen in that formula, there's 2 of them, so it's 15.999 times 2, which is 31.98 grams of O for that formula. So what we do next is we divide it by the mass of 1 mole. So if you go back to the prior slide, we found that the mass of 1 mole was 239.18. So we just added the 207.2 and the 31.98, and we got 239.18 grams. Then multiply that by 100. We have 86.63% lead and 13.37% oxygen. So that's the percent composition for PbO2. Notice that 86.63 plus 13.37 adds up to 100%. Your numbers when you find percent composition should always add up to exactly 100% or 99.99% or 99.98% or 100.01% or 100.02%. Anything else though, you may have done something wrong. So if you're not that close to 100%, go back and check your calculations. Ammonium phosphate, which we also did on the prior slide, we said that there were 42.03 grams of nitrogen, 12.12 grams of hydrogen, 30.97 grams of phosphorus, and 63.96 grams of oxygen. Look on the prior slide if you don't remember where those numbers came from. If you add all those numbers together, you get 149.08 grams. So take each of the numbers, 42, 12, 30, 63 point whatever, divided by 149.08 grams, multiplied by 100, we get our percentages. So NH43PO4 is 28.19% nitrogen, 8.13% hydrogen, 20.77% phosphorus, and 42.90% oxygen. Notice that we went to 2 decimal places with all of our percentages. Our percent symbol is our units when we do percent composition. And in this example for ammonium phosphate, it doesn't add up exactly to 100, but it does add up to 99.99%. Let's look at another example, zinc acetate. So from here, we have to first figure out what the formula is so we can find the percent composition. Zinc, even though it's in the D block, I told you have to memorize that it only has a charge of 2+. Acetate is a polyatomic ion, so that one has the formula CH3COO1-. So we're going to need 2 acetates for every 1 zinc ion. So the formula is Zn parentheses CH3COO parentheses 2. So now that we know the formula, we can figure out the percent of each element. So we list out the 4 different elements that we have. Be careful when you figure out how many atoms there are of each one. So there's only 1 zinc. Carbon, look at the formula real quick, see how many there are. Hopefully you notice that there's actually 4 carbon atoms, because there are 2 times 1, which is 2, plus 2 times 1, which is another 2, giving us 4 carbon atoms. Okay, be careful there. So 4 times 12 from the periodic table, or 12.01 grams, gives us 48.04 grams. Hydrogen, we're going to multiply the subscripts, 2 times 3, so we have 6 atoms of hydrogen, times the mass from the periodic table. Oxygen, we have 1 plus 1 times 2 for each, so we have 4 times 15.99 grams, giving us that many grams. Add those together, we get 183.45 grams. So we take each of these 4 numbers, 65.39, 48.04, 6.06, and 63.96, divide each of them by 183.45, and then multiply by 100. Those are the percents of each of those elements we have. So the percent composition of zinc acetate is 35.64% zinc, 26.19% carbon, 3.30% hydrogen, and 34.87% oxygen. All right, before we talk about how to find the formula for an empirical formula and a molecular formula, let's first cover what they mean, or their definitions. The empirical formula is the lowest terms formula, but the molecular formula is the true number and types of atoms in a molecule. And sometimes those are the same thing, but not always. So let's look at some different examples. We have glucose. The molecular formula, when you go to write out the formula on paper for glucose, you would always write C6H12O6. The lowest terms formula from that, though, is going to be whatever you can reduce it to. So we can reduce that to CH2O. Now that does not mean that glucose has the formula CH2O, because if you recall, the formula CH2 represents formaldehyde. We looked at that in our screencast in our last unit. Clearly, glucose and formaldehyde are not the same thing. So the CH2O is just the lowest terms formula of your molecular formula. Propane, C3H8. Well, you can't reduce that, so the molecular formula is the same as the empirical formula. Butane, C4H10, that can be reduced, so it becomes C2H5 for the empirical formula. It does not mean that butane has the formula C2H5, just the empirical formula for butane is C2H5. C10H8 can be reduced, so the empirical formula is C5H4. Sucrose cannot be reduced, so the empirical formula and the molecular formula are the same. Octane can be reduced to C4H9. So now we know the molecular formula is the true formula with the true number and types of atoms in a molecule. The empirical formula is the lowest terms formula. Let's figure out how to get them when they're not so easy like this table. So for finding the empirical formula, there's 4 steps. First step is finding the number of grams of each element. If you are given percentages, you can assume that you have a total of 100 grams, so that helps you figure out how many grams you have of each element. Then you convert each grams to moles. then divide each number of moles by the smallest number of moles, and then use the ratio to find the formula. So I have a little poem that I use to help me to remember this. And the poem goes like this. Percent to mass, mass to mole, divide by small, multiply till whole. Okay, let me say it again. Percent to mass, mass to mole, divide by small, multiply till whole. So that's what we're going to do. Here's our example. A compound is 45.5% yttrium, 54.5% chlorine. Find its empirical formula. So first step is find the number of grams of each. We're given percentages. So obviously 45.5 and 54.5 add up to 100%. So we can just change these from percent signs to grams. So we have 45.5 grams of yttrium, which is capital Y, 54.5 grams of chlorine, Cl. So that's step one, percent to mass. Next step is mass to mole. By the way, I would write down my steps that I'm giving you in the poem on your student notes, so you can look at that and refer to that to help you remember these steps. So to get to moles, all we do is we divide each one by the molar mass. You have to show your conversion here, grams per mole conversion, so number, unit, substance. When you do this, I want you to go to at least 3, if not 4 decimal places. So the reason we're going to 3 decimal places here is because we start off with 3. To avoid any issues with rounding, it's better to go to an extra number. So I recommend that you do that. 54.5 divided by 35.453. Again, you have to show all this setup like we do in our screencast here to get full credit. So that gives us 1.537. So here we did 4 sig figs, but 3 decimal places. I would tell you to always go to 4 decimal places when you do this. Okay, this isn't your final answer. You don't want to round too much, especially when we talk about such small numbers. We don't want to round too much because it can throw off our answers possibly. So I recommend going to 4 decimal places at this point. Now we've converted our grams to moles. We're going to divide each one of these moles by the smallest number. Well, which is smaller, 0.512 or 1.537? 0.512 is smaller, so we're going to divide each one by 0.512. Remember, by the way, when we have a number less than 1, it always starts with a 0. Don't start it with a decimal point. So when we divide by 0.512 for yttrium, we get the number 1. For the other one, we get the number 3. When you do this division, you should get a number that's really close to a whole number, or it's close to half of a number, or a third of a number. If you get anywhere in between, you probably did something wrong. So our ratio is 1 to 3. So therefore, for every 1 yttrium, there's 3 chlorines. So the formula, the empirical formula, is YCl3. Again, the poem, percent to mass, mass to mole, divide by small, multiply till whole. Let's look at another example. Here's our steps again. A ruthenium sulfur compound is 67.7% ruthenium. So how much sulfur is it? Well, 100 minus 67.7 tells us how much sulfur there is. Find the empirical formula. So ruthenium has 67.7 grams. Sulfur is 32.3 grams. Percent to mass, so we just did step 1. Mass to mole, so we divide each one by the molar mass. Show all these steps. Again, we go to 3 decimal places. I would go to 4 when you do this. Divide by the smallest number, which is 0.67. And then, because we can't have 1.5 sulfur atoms, we don't have fractions or decimal numbers in our formulas. What we're going to do is we're going to multiply the 1 and the 1.5, because we can't do that. We're going to multiply each of those subscripts by the number 2. And we get that formula. Here's our third example, all our steps. So we've got a 17.4 gram sample of technetium oxygen compound that contains 11.07 grams of technetium, find the empirical formula. So we know the total sample size, and of that total, only 11.07 grams are technetium, so the remainder is oxygen. So 11.07 grams of technetium, 17.40 grams minus 11.07 grams gives us 6.33 grams of oxygen. We start off with grams. We don't even start off with percent, and that's okay. Sometimes we'll start off with grams, and we don't need to go from percent to mass. Then we divide each one by the number of moles. Notice that in every single setup, we show you the conversion factors, and we have number, unit, substance every single time. Here we went to 3 decimal places. Again, I would go to 4 decimal places. Divide by the smallest number. So we get that fraction there, 3.5. We can't have that in a formula, so we're going to multiply both the subscripts by 2. And that is our empirical formula. Example 4. A compound contains 4.63 grams of lead, 1.25 grams of nitrogen, and 2.87 grams of oxygen. Name the compound. So here's our steps. We've got 3 different elements. We already know how many grams we have of each. So now let's divide by molar masses to get the moles. See, here we went to 4 decimal places, 0.0223. I like 4 decimal places, much better than 3. Now we look for the smallest number, which is 0.0223. So divide each number by that. And we get those numbers. So for a formula, we get PbN4O8. What in the world is that? Do we know how to name that compound? No. So what are you thinking? What could this be? PbN4O8. Does that look like you can do anything with it based on our screencast in this unit? Perhaps we could do NO2 and put that in parentheses with a 4 afterwards. And that NO2 then looks familiar. That looks like our nitrite polyatomic ion. So if you do that, you get this formula, which is now correct, and you should be able to name. Lead has multiple charges, so which charges does this one have? Well, it must have a 4 plus charge because the nitrite has a 1 minus. And there's 4 of the nitrites. So it's lead 4 nitrite. Remember the polyatomic ion, don't change its name or ending or anything, leave it as is. It has a Roman numeral because it's lead, and lead has multiple charges. All right, so we're on the 4th type of calculation in this unit, and it's the molecular formula calculation. It's not that bad. Let's look at the steps. First, you have to find the empirical formula. Then once you find that, you find the molar mass of your empirical formula. Then you find N, which is the molar mass of the molecular formula, which is going to be given to you. So that will be given, divided by the molar mass of the empirical formula. Once you have N, you multiply all parts of the empirical formula by N. N should always be an integer. It should never be less than 1. So what we're looking for is how many empiricals can you fit into the molecular to get the molecular formula. So I've summarized those steps at the top. Here's our example. A carbon-hydrogen compound is 92.3% carbon. It has a molar mass of 78 grams per mole. So the compound, which we're not sure of the formula yet, has this molar mass. So that's the molar mass of the molecular formula. So let's find the molecular formula. So if it's 92.3% carbon and it's only carbon and hydrogen, we know that there's 7.7 grams of hydrogen because our total percent is 100%. So percent to mass, so that's what we have here, 92.3 grams of carbon, 7.7 grams of hydrogen. This is for the empirical formula because we have to find the empirical formula first. Mass to moles, divide by small, so essentially that's 1 to 1, multiply till whole. We don't even have to multiply till whole because we already have whole numbers. So the empirical formula is just CH. So we've done step 1. Step 2 at the top of the screen, find the molar mass of the empirical formula. So carbon is 12.011 grams per mole, hydrogen is 1.008 grams per mole. When you add them together, you get 13.019 grams per mole. So that's the molar mass of the empirical formula. Let's find N, which is the molar mass of the molecular formula over the empirical formula. So when you're finding N, always remember it's the bigger number over the smaller number because I told you it cannot be less than 1. So this is N. So it's 6, so that means we multiply all the parts of our empirical formula by 6. So the molecular formula is C6H6. Example 2, we have a compound that has 26.33 grams of nitrogen, 60.2 grams of oxygen, and the molar mass is 92 grams per mole. That is the molar mass of the molecular formula. So let's find the empirical formula, then the molar mass of the empirical formula so we can find N and then our molecular formula. So we've got 26.33 grams of nitrogen, 60.2 grams of oxygen, divide by the molar mass. So percent to mass, mass to mole, divide by small, and then multiply till whole. They're already whole, so that's our formula. NO2, nitrogen dioxide is the name of that. So let's find the molar mass of NO2. It's going to be 46.005 grams per mole because nitrogen is about 14. Each oxygen is about 16, so 16 times 2 is 32, plus 14 is about 46, so that's where that number comes from. So we take the molecular formula molar mass, which is given to us, 92 grams per mole, divided by 46.005 grams per mole. We get 2, so we're going to multiply the subscripts by 2 and get N2O4. All right, last topic has to do with hydrates and anhydrous salts. An anhydrous salt is an ionic compound, which we already know we call those salts, that attracts water molecules and forms loose chemical bonds with them. We symbolize this by Mn, so that's our anhydrous salt. An is without, that's the prefix. Hydrous represents water, so that means without water. Uses of anhydrous salts are as desiccants. So when you go buy a pair of shoes, they often have those little bags in them with little beads, it feels like, inside. Those are just your anhydrous salts. They're desiccants. They dry things out to prevent any moisture and maybe smell or odors that might otherwise occur. Hydrate is your anhydrous salt, but it has the water attached to it. So it's hydrated. Just like when you drink water that hydrates you, the anhydrous salt with the water attached is known as the hydrate. So we symbolize it by this generic formula. This is generic. When we ask you for a formula, we don't want the generic version, we want the actual version. But this is our anhydrous salt, and in the middle here is a dot. Okay, you need that dot. The question mark represents a number, which you'll have to solve for, and then water. So let's say the number is 3. That just means that there's 3 water molecules loosely bound to the anhydrous salt. So 4 examples would be these. So that's our copper 2 sulfate. And then the 5 here, we use the same prefixes as we did before, pentahydrate. So the first example is copper 2 sulfate pentahydrate. This would be called barium chloride dihydrate. Sodium carbonate decahydrate. Iron 3 chloride hexahydrate. So Mn is just the first part, the ionic compound, and then dots, you see they all have a dot in them. The question mark is replaced by how many there are, the number, and then H2O. So to understand this a little bit better, we have our hydrate. So that's our ionic compound that has the water loosely attached to it. If we heat it up, as you might imagine, when you add heat, if the water is loosely bound to it, the water is going to separate. So you end up, after heating, with your salt that doesn't have water, but also you're going to have water separate from the salt. So that's what you're doing when you're talking about a hydrate and you're adding heat and then you're separating the water from the salt. So how do we find the formula? You're going to find the number of grams of your ionic compound or your salt and the number of grams of water. Convert your grams to moles. You're going to divide each number of moles by the smallest number of moles. For hydrates, the smallest number of moles should be the salt number of moles. So you should always have one salt for however many waters there are in your formula. Keep that in mind. And then use the ratio to find the hydrates formula. This sounds very similar to finding empirical formulas. So hopefully it's not too bad. Example 1, find the formula of the hydrate for each of the problems. So we've got the sample's mass before it gets heated. So that's the salt plus the water. That's our hydrate. Then after the heating, we have the anhydrous salt that's left over because when you heat, we know that the water evaporates. So all you're left with is the salt. So they're telling us the molar mass of the anhydrous salt is 85 grams per mole. So we've got 1.93 grams of our anhydrous salt. To figure out the mass of water, what we do is we take the salt and the water that we started off with, which was 4.38 grams. Then we subtract the salt, which is what we were left with, 1.93 grams. So whatever the difference is represents the amount of water that evaporated. So 2.45 grams of water evaporated. So then we're going to divide by the molar mass. Again, go to 4 decimal places. Divide by the smallest number. They're already whole numbers, so we don't have to multiply anything. So our formula, notice then that there are 6 waters for every 1 of our anhydrous salts. So the salt dot 6 H2O is the formula for this hydrate. Example 2, we've got a beaker. It's 46.82 grams when it's empty. Then we put the sample in before it gets heated, so it's the salt and the water. It's the hydrate. So beaker, salt, and water. And that has a mass of 54.35 grams. You heat it up, and the water evaporates, and you're left with just the anhydrous salt in the beaker. So that's 50.39 grams. They tell us the molar mass of the anhydrous salt is 129.9 grams per mole. So we have, of just the salt, 3.57 grams of our salt. How do we figure that out? If you take the beaker plus salt and you subtract the beaker, what you're left with is just the salt. So 50.39 grams minus 46.82 grams gives you 3.57 grams of the salt. How much water did we have? Well, if we take the beaker, salt, and water and we subtract the beaker and salt, what we're left with is just the water, 3.96 grams. So 54.35 grams minus 50.39 grams leaves us with 3.96 grams of water. So it's really important you kind of think about what's happening in these situations with the hydrates to understand where the numbers come from, because you're going to have to figure those out on your own. If you keep in mind that you start off with your hydrate, which is your salt with the water loosely attached. After you heat it, the water will evaporate and then you're just left with your salt. So we know how many grams we have of each. We're going to divide by each one's molar mass. So that gives us these numbers to 4 decimal places and 3 decimal places. Again, I would go to 4 every time here. Divide by the smallest number. Those are whole numbers, so we know there are 8 water molecules for every one of our salts. So Mn.8H2O is the formula. Let's look at a third example. We've got our beaker, and sample. Remember, the sample is the salt and the water. And then after heating, we've got the beaker with just the salt left in it. They give us the molar mass of the anhydrous salt. So 4.20 grams of the salt. Again, we get that from beaker plus salt minus beaker gives us 4.20 grams. For the water, we get that by taking the beaker plus salt plus water minus the beaker plus salt. That gives us 2.36 grams of water. Divide by molar mass. Go to 4 decimal places. Divide by smallest number. We get whole numbers there, 1 to 4. So for every 4 waters, there's 1 of our salts. So the formula is that. So it's a tetrahydrate. Now it asks us for the previous problem, find the percent water and the percent anhydrous salt by mass. Got to do a little bit thinking here, but this was the formula we had on the prior slide. So to get the percent water, we can take the grams of water in our formula divided by the mass of hydrates. So 4, because we know that there's 4, so that's where that number comes from, waters in the formula, divided by the total molar mass of the hydrate, so that's the water plus salt. So the water is 4 times 18, the salt was 128. So multiply that by 100 after you add and divide, and you get 36.03% water. 2 decimal places, just like we did for percent composition. So if it's 36% water, subtract that from 100, 63.97% is the anhydrous salt. There's a second way you could do this. You could say, based on the numbers that we got from massing it out, because we would have, if we were in lab, put this on a balance to find the mass of each one. So when we had like the beaker empty and the beaker with the sample in it, so the beaker with the sample in it, and also the final beaker with the anhydrous salt in it. So from the prior slide, we saw that we had 2.36 grams of water. So we take the grams of water divided by the total mass, so that's 2.36 plus 4.20, then multiply that by 100, you get 35.98% water, subtract that from 100, and that gives us 64.02% of the anhydrous salt. These numbers are very, very close to each other, which they should be. They are not exactly the same number, and that's due to rounding of our molar masses and rounding when we measure. But those are really close to each other, even though they're not exactly the same. So those are both perfectly good ways to calculate this, and whichever one you would use would be based on the information you have in your problem. Next one, strontium chloride is an anhydrous salt, right? That's an ionic compound on which the following data were collected. Find the formula of the hydrate. So we now know what the ionic compound is. It's strontium chloride, so we're not going to be writing Mn anymore. So our beaker has a mass of 65.2 grams when it's empty. You put the sample in it. So the sample is the hydrate, which is the salt plus water. And then you heat it up and the water evaporates and you're left with just the salt. So if we were to do our calculations, we would have 73 grams of salt. So that's 138.2 grams minus 65.2 grams. Then 49.7 grams of water is the 187.9 grams minus the 138.2 grams. Next, you'll divide by molar mass, but you first have to figure out what the formula is for strontium chloride. Strontium's in group 2, so it forms an ion with a +2 charge. Chlorine's in group 17, so you get SrCl2. So that's your salt. This is that. So if you look up on the periodic table, for 1 strontium atom and 2 chlorine atoms, you add them together, you get 158.52 grams in a mole. And really, you should be putting here SrCl2 because you actually know what it is instead of Mn. And then water is 18.02 grams in a mole. Again, go to 4 decimal places here, not 2 or 3. Divide by the smallest number. Those are both whole numbers, so we now know that it's strontium chloride hexahydrate. So do not put Mn.6H2O. If you know the name of the compound or the formula of the compound, you need to include that formula in these calculations and in your final answer. All right, that's it for this unit. Thanks for watching. Have a great day.